Thanks so much. Hi, everyone. I'm Tina. I'm a PhD candidate here at Caltech, and I'm excited to share some of the results from a paper of mine that I just submitted and is now in review, talking about some more of the sedimentological context for these magnesium sulfates. So my talk is going to be divided into two parts. The first part, I'm going to kind of give more of a look at some of these diagenetic textures, including the nodules that William set up so nicely, and kind of get you a better perspective on what these features are that we're looking at and what they can tell us. And then we're going to go kind of more to a basin scale and think about the different potential formation mechanisms. William just laid out one really clearly and very nicely, and we'll think about some of the other possible options that we have. So I can kind of zoom through this since we just got that great overview of context, but again, we're in Gale Crater, and I like this cutoff artist rendition a lot because it just reminds you that Mount Sharp is made up of these flat-lying strata, and below some certain point we had orbitally defined phyllosilicate-bearing strata that was then confirmed on the ground, and then above that the sulfate-bearing strata. And so my study really focuses on that transition between those two units. And so I've given you kind of our rover traverse with the highlighted region I focused on for my paper. This is between the Mary Anning and the Canaima drill targets, if those are familiar names to you. Mary Anning is down at the bottom here, and then we moved about 200 meters uphill to Canaima. So that gives us a nice 200-meter stratigraphic section, although we did do this big lateral traverse around a scary sand trap. So that gave us a nice good look at some of the lateral variation in these units at the same time. I mostly focused on imagery from the MOLLE instrument. That's our hand lens approximate on the rover that takes really nice up-close pictures of these nodules so we can kind of unpack what they look like a little bit better. And what we found as we drove across this region was we started to see this amazing suite of diagenetic textures, not just nodules, but color splotches. I love this one. We drove over these rocks and broke them open, and then we saw these beautiful color splotches underneath, veins and different zonations of color that really increased in abundance as we drove through the bottom part of this the traverse region. And then after we went to Montmercou, which you may hear about at other points in this conference, it's kind of a sandier body interpreted to be more like a channel. So you're moving from deeper lake fine-grained deposits out towards the lake margin. And then up above that, as we transition into more of the coarser-grained, sandy aeolian deposits, we saw the nodules really dominate. So those other diagenetic textures went away, and we only saw nodules in lots of different scales, and they also started to overprint the primary stratification. So here you can see there's a few places in here where you can make out parallel lamination, thin beds, but most of these outcrops are totally overprinted by these nodules. They don't ever disrupt the lamination, like having a lamination go over them, so they didn't seem to be forming at the same time as the lamination, but rather overprinting those laminations. There are other places where they seem to be organized in different ways. William showed a great example of the polygons and some of the other shapes. Here I've just shown on the bottom an example of places where they're kind of spaced out as if they were kind of pushed by a front that moved them along. So the key here that I found when I looked at the distribution of these different features across the rover traverse was that there did seem to be a correlation with the grain size of the sediments that we were seeing and where we saw the different nodules, which will link to a lot of thoughts I have about the porosity of the rocks and the permeability as groundwater may have moved through them. And so I'm going to jump one slide ahead here. And so I wanted to think about the bigger scale chemistry. So the ChemCam instrument can shoot the laser at individual nodules, which is amazing. and told us that individual nodules contained magnesium sulfate, but there's variation in those measurements, and I wanted to try and relate it a little bit better to the bulk rock measurements because we can't drill into individual nodules. So I did that by correlating with the APXS instrument, the alpha particle X-ray spectrometer, which goes down onto the rock and measures a couple centimeters across circle. This is a generalized correlation because I was just categorizing each rock based on how many nodules were on the entire rock, not individual nodules within the APXS spot. That's kind of a more challenging deconvolution that could be done in future work. But what I saw here, so we've got our stratigraphic column on the left as we're moving from bottom to top through our different rock types. And you see we got our finer grain down low, and then we've got the coarser stuff above with some nice lenses. And the darker colors are more nodular targets. And as we moved up in our section, we saw that the more nodular targets also had a higher magnesium and sulfur signal and less calcium. So that kind of brings us to this link that the magnesium sulfate, as shown in the bulk rock data, also is concentrated in those nodules and pore-filling cements that are kind of holding those nodules together. So the story here that I was thinking about is the magnesium sulfate in these nodules and then where that links up with the stratigraphy as a whole. So I'm going to zoom us out and think a little bit more about a basin scale perspective. Gale is a really interesting basin. It's the lowest point around, and that means that there's really interesting things that could be happening with the groundwater here. I spent a long time digging into terrestrial literature, looking at places where you could precipitate sulfates at depth, and I found some great analogs, not with magnesium sulfate, but with calcium sulfate. And so I'd like to explore that a little bit with you. So this first point is just to kind of demonstrate that these amazing diagenetic textures that we see in their distribution are pointing to a pretty complex hydrological system that we're dealing with. And so I think that begs for a creative explanation, and I think it's important to do our due diligence and think about all of the different formation mechanisms that could be at play here. So I'll present 4 hypotheses. The first one, I can go through pretty quickly because you just heard a whole talk on a big piece of it. So the first idea is that we have all of these really cool polygons that we could be concentrating these sulfates in evaporite scenarios. This also kind of links with the detection of starkeyite in the Canaima drill hole. Starkeyite on Earth pretty much is only ever found in efflorescent environments. And so I think this is a really good model for a lot of the places that we're seeing like these maybe dunes with interdune playa lakes where we can be concentrating things and creating wetting and drying to concentrate these sulfates. But the other thing I think is important to think about is what we see in the whole area that I've studied, right? So this is a great explanation for some local examples, but there's some things that we don't see that I think would be a really smoking gun for this hypothesis. So on Earth, in evaporitic crustal environments, when you've got water drying up and leaving salts on the surface, you end up with things like a dissolution collapse breccia, where you might dissolve away those salts and rocks collapse into it. TP structures are a classic. We've got a nice modern and rock record example where when salt crystallizes, it expands and creates these formations. And then on the right here, crystal growth displacing lamination. So salt crystals can grow and actually cause those laminations to deform and drape around them. So these are just some examples of things that we've been looking for, but we didn't find in any of our traverse through here, excuse me. And I think that that is a really important key here when we're thinking about the sedimentological evidence, not just the chemical evidence for what we're seeing with these sulfates. So that's what brought me to think about some of the other possibilities if we weren't for all of the sulfates we're seeing, if we're not concentrating them at the surface. Are there ways we could get them down at depth? So I'll present 3 options for that I've been working up. The first one is a top-down scenario. So imagine we're going through our stratigraphy and we're building up this aeolian sequence, and water level may be rising and falling, and we may have some lakes outcropping on the surface, bringing us those beautiful wave ripples. And then over time, we'll dry out more, but at some point, there could be big bedded evaporites, the stuff that we haven't seen the smoking gun for. That could be up at the Boxwork horizon, which is a place where we're going to get to soon-ish with the Curiosity rover. Could be something else that we haven't seen from orbit. And then over time, as we're evaporating at that higher up surface, your gravity-driven dense brines are sinking down, and because of local heterogeneities in the sediments and those grain size differences and how things are compacted locally, you can create places where the sulfates could precipitate out in pore spaces at depth in different zones. I like this idea because it has a lot of links to the stratigraphy and the different units we've gone through, but its limitation is that we don't know yet what might be above us that could be bringing salts down, so yet. Our second option, we're gonna go bottom up for this one. You saw this figure this morning at the plenary actually, and I'm gonna have you ignore all the details about the different rock types that have filled in Gale Crater, but just think that early Gale Crater could have had an evaporitic system that left some deep buried bedded evaporites. Then you get meteoric water that comes down from the crater rim or the central peak, wells up through those salts, dissolves them, either driven by leftover heating from crater impact or geothermal gradient, and then wells up, supersaturated, cools to a point where we can precipitate in the region that we've been exploring stratigraphically here. And then lastly, another top-down method, but we're gonna think more globally about the aridification of Mars. So here, this figure, now we're in the time period where we're building up just dry aeolian strata on Mount Sharp, and the groundwater, the surface water has evaporated, and so the groundwater is permeating up through those sediments. Groundwater table is dropping. It's dropping at time 1, it's dropping at time 2, getting more concentrated, and then it drops until there's a point at which it starts to precipitate because it's so concentrated, again, nucleating in pore spaces in the rocks. So I'll zip through these takeaways, just that our nodule distribution correlates really well with the permeability and pathways of the different sediment types that we've observed along this traverse in the Mirador Formation. It does seem from multiple instruments that magnesium sulfate is concentrated in the nodules and cements, and it may not just be that they were evaporates on the surface, because there's a lot of sedimentological evidence that we don't have the signs to show us exactly that. So I've provided some fun alternatives as food for thought, largely informed by models that I've thought about on Earth as well. And so with that, I'll put in a shameless plug that I'm graduating next year and would love to talk to anyone this week about postdocs or jobs, and I'll leave it there.
Thank you, Tina. If we have one quick question, head down to the mic. And I wanted to ask Tina, is this process you talked about for magnesium sulfates only, or could the calcium sulfates also be behaving in this? And yeah, so think about that, and then we'll get to this other question.
Sure, yeah, there's solubility differences. And so magnesium sulfate is so soluble, which is part of what makes this an interesting problem. And so for a lot of these, we're thinking about, like on this third one, like the last gasp of water when you're so concentrated, and so you can precipitate out these really soluble salts. And so in those cases, you'd be kind of filling veins with calcium sulfate before the magnesium sulfate precipitates. But I think there's a lot of cycling of groundwater, and that's what's bringing both the calcium sulfate and the magnesium sulfate into these systems, for sure.
That's good. Go ahead.
James Haber, Smithsonian, great talk. You mentioned briefly about permeability and porosity of these rocks and how, the nodules are concentrated in the coarser grain stuff, I think. Does sort of the permeability and porosity of the rocks nearby have any sort of indication of, whether the fluids are coming from above or below, why the nodules are sort of concentrating where they are, if that has provided any insight?
Yeah. So it's more we've got coarser grains on top and finer grains below. And then below my section is where we have Glentorrhodon, right, very clay rich. And so I think it's not unreasonable to think Glentorrhodon it's like a lot of clay, it could act kind of as an aquiclude. And so if we were going from top down, then part of the reason we see this amazing zoo of diagenetic textures right above Glentorrhodon could be because these salts are percolating down and the water's percolating down and get stuck. And so for a long time, you could have these waters, permeating through and creating things like that. But you could also fracture Glentorrhodon and move salts up through and then fill those fractures with calcium sulfate veins and then let it percolate above. So it's a little hard to differentiate, but that is a big part of the pieces in here. Great question.
Cool stuff. Thank you.
Thank you. Let's thank Tina again.